So finally, having fitted the model, we wanted to conduct the model diagnostics and check for the assumptions. There are these three assumptions. The first is four assumptions. The first is the linear model is appropriate, and so that we can judge by looking at the scatter plot of the y's against x's, and that should be roughly a straight line. The other better plot is the scatter plot of residuals, standardized residuals are better against fitted values, and this plot should be patternless. I think I'm seeing the same thing in both. Sorry, and this, the last one is, sorry, is the standardized residuals against the xi's, and again that should be without pattern. For the normality assumption, we can either look at histograms of residuals as before, or the normal probability plot as we did before in another case, or we can look at some other tests for normality, which we won't bother with. So these two residuals plots and the normal probability plot will be adequate as we have did before. For the constant variance term, the bet again is those two plots we had before, standardized residuals against fitted values and standardized residuals against xi. Again, both of these should be without pattern. So we saw in the another case, what we discussed was this idea of fanning in and fanning out. Those kinds of things would suggest some systematic change in spread of variance with respect to data values, and otherwise also we can look at histograms. And finally, errors are uncorrelated here. We do have some tests, but we won't bother with those. We won't actually be looking at the idea of uncorrelatedness at all in this. So looking at those ideas, evaluate this model here. You'll find here the scatter plot looks fairly straightforward. Nice straight line there. Histogram looks fairly normal. The normal probability plot is fairly straight. There's no significant departure or serious departure from straight line. And the residuals against fitted values here behave themselves fairly well. So this model is okay on all counts. Normality is okay, the equal variance looks okay, there's no change in spread here, and the linear model looks okay as well. If you look at this next one here, what you'll find is in the plot of the y against x's, there's a very slight curvature here in the plot. So that curvature indicates the linear model might be appropriate. If you also look at histograms, there's some skewness there, and of course you see also here in this particular plot here a certain pattern. This certainly shows it's not normal, but the basic problem is that the linear model here is inappropriate. Once you fix that part, maybe the rest will also be okay. And how do you fix this kind of model here? Well, we'll see this in the next part of these slides. There are ways of trying to fix when we get these kinds of patterns. How do you then fit a better model? Looking at the next one here, what you find is that the linear plot is fine, the straight line plot seems okay, linear model seems okay, but there's some problem with the histogram over here. It shows you some skewness, so it might not be normal. The equal variance thing is okay mainly by and large. So here the problem is that the normality assumption fails. So it doesn't look as if that the data, actually the observed values, are normal in this case. And again, how do we fix that? We'll see this afterwards. And finally, if you look at this, the clear problem is, well, look at the histogram, it doesn't look very normal at all. But that's not the problem. The basic problem seems to be there's a huge change in spread. So you get this big fanning out idea here. So equal variance assumption fails. And again, as I said before, we'll see how we can fix these kinds of problems when we have these situations occurring in our data. All right, finally we'll get to these points of high leverage. So outliers and high leverage, both of those. Outliers are points that are away from the bulk of the data, and they usually have very large positive or negative residuals. And so if we take a look at the plot of standardized residuals, then if the standardized residuals are 2 or more away, -2 or less, or 2 or bigger, that would indicate or identify these kinds of points. Now, the way to estimate the effect of outliers or investigate the effect is to regress or fit the model with and then without them, and then see what the difference is. And if you do that, you must report what you've done, because often people will take away these outliers and get a very good model, but they're cheating because, first of all, they are removing some data that has information maybe on some systematic structure of the data, and they are reporting that. And secondly, they have only improved the model because of the outliers. And the outliers, if they haven't been investigated, again, will be losing those people and not being able to pick up any systematic problem with those. Points of high leverage are the opposite. They are those points that have very small residuals, and they have a large influence on the goodness of fit. And again, we should refit the model without those. As an example of a point of high leverage, here's some data. Now, most of the data here is essentially doing nothing at all. It's just that point there that fits the model. You can see that the line goes through that point. If I deleted that point, my regression will be quite different. In fact, if there's anything at all there. So here is a point of high leverage. This one single point determines the regression. And finally, correlation coefficient. We saw this before. This is essentially a measure of the strength of linear relationship. So essentially, it's 1 minus the residual sum of squares over total sum of squares. Now you can see that the residual sum of squares here is large. Sorry. If the residual sum of squares is large, that means that the correlation will be 0. That's nothing much to talk about. But if the regression sum of squares is large, this will be close to 1. So R squared lies between 0 and 1, and R lies between -1 and 1. And this is a measure of the strength of a linear relationship. Be careful, because you can often get situations where the relationship isn't linear and you're getting a 0 coefficient there, but there is some relationship still. So as what's going on here, the idea, as we said before, was that if R is close to an absolute value, strong relationship, because in that case, the total sum of squares is about the same as the regression sum of squares. On the other hand, if the regression sum of squares is small, that means that R will be close to 0, and there's nothing particularly interesting to talk about there. And as further on, you can find that out for yourself. R actually becomes B1 times SSX over SSXY square root of. So you could, instead of doing hypothesis tests for B1, do a similar hypothesis test for R. They're the same in principle, equivalent. We won't do that here, though. And finally, the caution, as I said, was large R means a strong linear relationship. It doesn't mean it's the best. It certainly doesn't mean that X causes Y. Causation is a more difficult thing to prove. It could be that X and Y are both related through some other variable that hasn't been observed, isn't in the model at all. And again, R small in absolute value doesn't indicate no relationship at all. It just means that there is no linear relationship. There could be still no linear relationships. And if you reject H naught that beta equals 0, that means there's a significant linear relationship. It does not mean that this is the best one or even an inappropriate one. We need to perform some model diagnostics. So here's an example of data XY that have 0 correlation. R squared is 0. But there is still a very strong relationship between X and Y. It's by a circle, yeah? So this is a non-linear or non-straight line relationship. So R being 0 does not mean there is no relationship at all. You must always examine plots of the data. And finally here, we'll take a look at the detailed analysis of Pharmax data in the next lecture.